This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
Good evening and welcome to the Jeffrey B. Graham Perspectives on Ocean Science Speaker Series. My name is Cheryl Peach and I'm a program scientist here at the Birch Aquarium at Scripps Institution of Oceanography, UC San Diego. It's a great pleasure to have you here this evening for this very special Perspectives lecture, and it is my great pleasure to introduce our speaker, Dr. Margaret Leinen. Margaret. Margaret is the Vice Chancellor for Marine Sciences at UC San Diego. She's the Director of Scripps Institution of Oceanography and the Dean of the School of Marine Sciences. She joined Scripps in 2013, and she brought with her a wealth of experience in ocean science, academic leadership, and federal research administration. Now, I could spend quite a long time introducing Margaret with a long list of her many awards and many accomplishments, but you're going to have to settle for a few highlights. So Margaret served for 7 years at the National Science Foundation as the leader of the Geosciences Directorate, as assistant director, and the coordinator of environmental research and education. At the National Science Foundation, she oversaw a budget of $700 million and was overseeing and presiding over climate change research planning, as well as directly influencing some of the most consequential programs in marine, atmospheric, and earth sciences. In addition to her role as the leader of Scripps, she's currently serving as the president of the American Geophysical Union. This is one of the foremost professional societies for earth, ocean, atmosphere, and space sciences researchers from around the globe. She's also a fellow of the American Geophysical Union and the Geological Society of America. So I could go on, but I'm going to stop now and ask you to join me in welcoming Margaret and her talk titled Research at Scripps Oceanography, Understanding and Protecting the Planet. Margaret, thank you so much for being here.
Thanks, Cheryl. It's wonderful for me to have the opportunity to talk to all of you. I've attended several of these Birch Aquarium Perspectives lectures, and I've enjoyed them so much. So I hope that I can give you a perspective that on Scripps as a whole that you'll enjoy. So, you know, most of the time when I'm on a plane or someplace else where I meet somebody from the public and I say that I'm an oceanographer, they ask me one of two questions. Do you scuba dive? And do you work with marine mammals? And I don't do either. But I am still an oceanographer, and I think that one of the things that most of our oceanographic institutions really represent, and that many, many people don't understand, is that in spite of our name as Scripps Institution of Oceanography, much of our work involves the solid earth, the history of the planet, the history of the oceans, the atmosphere, and even the earth from space. So this wonderful animation that you're seeing from NASA, it gives us a perspective on the currents and the motion of the ocean. And that's very much a part of what we do as well. About 2 months ago, the researchers at Scripps went off to a retreat to talk about research directions for the future. And the ground rules were that you had to talk about something that you couldn't do on your own. You had to have partnerships with colleagues either here at Scripps or elsewhere, and that they had to be really big ideas. And so what I'm going to talk to you a bit about is some of the big ideas that the faculty at Scripps are interested in pursuing for the future, and some of the things that I think you're going to be hearing more about. And it's nice that right now, we're focused there on Antarctica. It's moving out of the screen and we're seeing Australia, because one of those areas that the faculty want to focus on for the future is the poles. And Scripps institution has a long history of working in polar regions. This particular slide is Jeff Severinghaus, one of our chemists who studies the chemistry of small bubbles of air trapped in ice cores to understand the history of climate. But our involvement with polar studies goes very far back into Scripps history. One of our early directors, Harold Sverdrup, was actually the scientific director of the North Polar expedition of Roald Amundsen on the Maud, 1918 to 1925. And Sir Charles Seymour Wright, who was on Scott's famous expedition, 1910 to 1913 in the Antarctic, became the head of Scripps Marine Physical Lab in the 1950s. And through that long history, we developed our polar studies program during the 80s, and that's a vibrant piece of what we do at Scripps. Not just studying the ice itself, but the ocean under the ice in the Arctic, the biology of the area, the geology of the area. And one of the reasons that the Scripps faculty are very interested in new experiments and new work in this area is because the polar regions are undergoing dramatic changes. So this illustration is a cartoon based on our satellite observations of the ocean, the Arctic Ocean. And the white part here is the ice-covered part of the Arctic at its minimum during the summer. So, and the yellow line that you see around here is where that extent of sea ice was in the Arctic when we started looking at the Arctic with satellites in 1979. And the portion that you see here was in September of 2012. We've lost 40% of the ice cover of the Arctic Ocean during the summer months. During the winter, it's ice covered, but during the summer, more and more, we're seeing a decrease in the coverage of ice. Some of the other areas, like Greenland, the ice cover on Greenland is shrinking rapidly as well. And the color coding here is for the rate of decrease since 2003. So while the top of the highest portions of the ice in Greenland and the middle of Greenland is still not melting very much, the areas around the coast of Greenland are melting much more rapidly. And this little graph over on the right-hand side shows you the drop-off with time from 2003 to 2013. So just in the last decade, we're seeing remarkable changes in the ice cover on the Arctic and Greenland, and the Antarctic as well. So here, the most rapid changes are on the Palmer Peninsula. That's the part that sticks up towards South America, and over here in the West Antarctic. And the Ross Sea is here and the Ross Ice Shelf down here. So this is again from 2003 to 2013, and here's the average mass of ice loss with time. So we're losing about almost 100 gigatons of ice per year on Antarctica. So why are we worried about those dramatic changes? They imply big changes for us. First, all of that, especially Greenland and Antarctic ice, is ice that's currently going into the ocean and resulting in sea level rise. So that's part of the increase in sea level that you've been hearing about. And we'll talk a little bit more about sea level later on. But the other big impact, especially in the Arctic Ocean, is that as the ocean becomes covered less with ice, it's less able to reflect sunlight back into space. So during the summer months, there's more sunlight coming in to warm the Arctic Ocean, and we're seeing changes in the Arctic itself, in the ocean itself, as a result of that warming. And so that's a feedback loop. The Arctic Ocean becomes warmer, it's less able to support ice during the summer. So these are the areas that are seeing the most rapid change. And these are the areas that the faculty at Scripps are really interested in focusing on over the next few years. Not only the ice, certainly the ice itself, but not only the ice, also the oceans around the ice and how the ocean interacts with this. So I'll give you one little example of something that is going on right now. During November, a group of scientists led by researchers at Scripps, by Peter Bromirski, went to the Ross ice shelf. So here's the Palmer Peninsula again, that's sticking up toward South America. And here's the Ross ice shelf, so a huge ice shelf, ice floating on water. And that ice shelf is so thick that when you look at it from an airplane, you can see it, that's about 100 feet cliff of ice, and there's even more below the water line. So this is a huge tablet, a huge thickness of ice. But we know that it is responding to changes in temperature, in the formation of ice and the flow of ice, and we're very interested in finding out how it's changing, and especially how the ocean underneath that shelf of ice is changing with time and how it's influencing the ice shelf. So what Peter Bromirski and his colleagues did was apply their tools for studying seismic movement to the ice shelf. So Peter is a seismologist, and they actually went out to the 16 stations across the entire Ross ice shelf and put in seismometers. So this is a pole that tells them where the seismometer is, and buried here in the ice is a seismometer which is recording the movement of the ice and how it's being affected by tides underneath, how it's being affected by waves which can actually move in and influence the water under the ice, and how that is related to the motion of the ice shelf itself. So during November and December, they put in 16 stations. They went to all of them and recorded data after they were put in to make sure everything was working properly. And then they came home to wait next year when they'll go and collect all of the data. So this, you can imagine, so think about the Arctic winter coming on, and the Antarctic winter coming on, turns dark, and these sentinels of motion of the Ross ice shelf will be there recording for Scripps oceanographers. And what they're very interested in is how the motion of the ocean itself affects the stability of that ice shelf. So something that all of those people that ask me whether I do scuba diving and whether I study marine mammals certainly wouldn't be thinking about, this sentinel in the Antarctic there in the Antarctic winter, but a very, very important piece. And just one example of how all of the fields of science at Scripps are focused on looking at these big problems. So let's look at another one, also not in the range of scuba diving. So in the 90s, physical oceanographers proposed a very ambitious experiment, and it was to take a snapshot of the entire ocean, surface to bottom, all at one time. And of course, we didn't have the ability to do that. And what they were really focused on was being able to have a baseline to study change in the ocean. And in order to do that, they had to have measurements all over the ocean and from surface to bottom. So they designed an experiment called the World Ocean Circulation Experiment. And the lines on the map show the tracks of ships which went across the ocean measuring in the water column as they went. And this experiment, this grand snapshot of the ocean, took almost a decade to complete. It cost more than $100 million to do. An extraordinary effort, not just by the US, but by the entire world oceanographic community, an extraordinary experiment. Come forward a couple of decades, and we're redoing that experiment in a very interesting way. So here at Scripps during the 90s, there was an effort to develop a new way of taking measurements. I should say when those measurements taken from ship were conventional. I should have put a picture in of the water sampler, which is a huge rosette of individual water sample containers, which is lowered to the ocean floor, then brought up sampling as it goes. Instead, we developed the concept of being able to do that without a ship. And that concept was to use a float. This one is called the Argo Float. And I think that you've had some presentations on it. And Argo is a free drifter. And inside of the Argo Float are the instruments which allow us to measure the temperature, the salinity, the pressure, the depth, in some cases the oxygen content of the ocean, and to do it remotely. And so the way this works is that a ship, usually a bigger ship than this, goes out, throws an Argo float over. It sinks down to about 2,000 meters depth, about 6,000 feet in the ocean, moves along with currents, and then it comes up to the surface. And as it comes up to the surface, it measures all the way up and then sends its data back via satellite to us on land. And this idea was adopted by the oceanographic community as an experiment for a new way of being able to take those views of the ocean. And Scripps here took a leadership role in convincing the world to try this technology and to invest in it. And so this little map is going to show you the evolution of the Argo Array. So this is June of 2001, and at that time there were 194 of those floats in the ocean, and each little dot you'll see represents a float, and the little red tail behind it is about a week's worth of travel of that float. So now what you're going to see here is the population of the ocean with Argo floats. We're at 2004. Right. Looks like insects, doesn't it? 2007. We're up to 3,000 floats. And what we're going to, when it stops, we're going to be at the end of end of March of 2014 with 3,600 of these floats. Right now, we're almost at 4,000. So the entire world has purchased and contributed to this vast array. And that array makes more measurements of the ocean in a year than that entire world ocean circulation experiment made. And it's an extraordinary look, and it's no longer just a snapshot. It's an opportunity to look at this constantly. And what's come out of that? I'll give you one example. A terrific result has been that we've been able to measure the heat content of the entire upper portion of the ocean, the entire upper 6,000 meters. And what we've seen is that through time, that heat content is increasing. It's it's not just the surface of the ocean, but the entire ocean is warming. And this was a very important result because there's been a huge debate in climate studies because the surface skin of the ocean has not increased a lot in temperature over the last 12 years. And so there's been a sense that, well, maybe climate isn't changing that much. Maybe we're not heating up the world that much. And what the Argo Array tells us is that that heat is going into the ocean and heating up not just the surface, but the entire ocean. And in a paper just published last week in Nature magazine, we've been able to look at the distribution of that warming of the ocean. And here the red are warmer areas, the blue are cooler areas. And as you see, there are more orange ones than there are blue ones. But one interesting thing, if you look, there's the equator. And if you look, there's more heat going into the southern part of the ocean than there is into the northern part of the ocean. So fundamental differences about how the ocean is taking that up. So contrast that with the best of our capability during the 1990s to be able to look at the ocean. A wonderful snapshot. It was revolutionary, believe me, but now the fidelity that we're able to look at in the time series and our ability to view the ocean. And observing is the first step to understanding. Scripps, responsible for both the development of this wonderful instrument and convincing the rest of the world to take on this array. So another great area that we're very interested in, and what comes next, remember I said that these only go to 2,000 meters. And of course you know that the deepest part of the ocean is much greater than that. And so of course we're working on the next step, which is called Deep Argo. And it's an instrument that can go all the way to 6,000 meters. Why didn't we do that in the beginning? Because it's very difficult to develop an instrument which can take the pressures of 6,000 meters and go up and down the differential pressure and also be stable enough to make those measurements. But we've made that technological leap now. So stay tuned. You'll soon see Deep Argo. So I said that we would come back to sea level rise. And this is another area of great interest at Scripps, and one of the areas that was featured during our retreat. So our scientists said, let's look at what's happening with sea level rise. Remember I said that ice on Greenland and Antarctica and all of the land-based glaciers were melting, were contributing to sea level rise. And as Cheryl said, I came here a little over a year ago from Florida. So that's Miami. That was in my backyard. And in Miami, during even sunny days like this, if it's a high tide, they're experiencing flooding from sea level rise. In South Florida, we call this sunny day flooding. And that's the ocean coming up into downtown Miami. But it's not just low-lying areas like that. This is the beach here in the North Del Mar area during a severe storm. And the difference between this light color up here and this darker color, that's the water line from a severe storm. And to remind us that, you know, even if we built our houses up at the top of the cliff, the water is impacting that cliff and can result in erosion like that you see here. So what's happening in this area? This is a projection from the last Intergovernmental Panel on Climate Change assessment of climate change and climate change impacts. And what it is a projection into the future using a number of different scenarios about sea level rise. So this is 2000, 2100. And here we are at the time that they started this work, so that's about 2010. And the most conservative model of climate change and how much CO2 we're going to put into the atmosphere is this blue line. And the upper ones here are what happens if we don't take any measures toward decreasing greenhouse gases going into the atmosphere. So essentially this is saying somewhere between, that's 4/10 of a meter, so basically, you know, 1.5 feet up to maybe 2 to 2.5 feet by the end of the century on average. So how does that play out, and where does Scripps play in that whole realm? One of the things that scientists here at Scripps have focused on is how that sea level rise will be distributed around the world, because the ocean isn't really like a bathtub that just rises all at once. And what you see here are the regional trends in sea level rise from January of 1993 to May of 2014. And these red areas are the areas that are increasing in sea level, and the blue ones are decreasing. So you see we're actually at almost zero. So we haven't been experiencing much of this, while the Western Pacific has had much more rapid sea level rise. So even here in Miami, where I said we were experiencing all of this change, is right on the cusp. Why do we think this is? We think this is part of a larger scale decadal change in the ocean, and that during the last couple of decades, we've been in a state of the ocean that has sea level rise focused on the Western Pacific, but that will switch to a state that has sea level rise more focused, not exclusively, but more focused in the Eastern Pacific over the next couple of decades. So that says that's something that we have to be watching out for. So remember I said sea level rise may be 1 foot, 1.5 feet, 2 feet by the end of the century. So, you know, why should we worry that much about 1 foot, 1.5 feet? The reason is that the big danger is not just the inundation or the slowly rising sea level, but also what happens as a result of storms. So I'll explain this complicated diagram. So this is California today and in the future. So here's sea level rise today, and we'll just call that 0. And here's the projected increase in sea level. But superimposed on that are all of these variations that have to do with decadal changes in the ocean. So we might see sea level varying over that time as a result of El Nino, other large-scale changes. Then superimposed on that are what happens during extreme high tides. So if you've experienced king tides here, you can see dramatic changes in the lagoons, I've seen them right out my window at Scripps, the difference between almost no beach during a king tide and very broad beaches during times of lower tide. So we have to add to the sea level rise the extreme high tides. And then on top of that, during severe storms, think about the 1982 El Nino and the severe storms that we had at that time, that storm water pushes up a storm surge onto the coast, and that extreme storm wave setup and run up can push sea level rise impacts much higher than that. So what we've been used to here and elsewhere around the world is sea level with a certain degree of high tides, and we've taken that into account as we built things, and as we see 100-year storms like we thought 1982 was, we've adjusted to that. But what we're going to see in the future is that plus the sea level rise. And that's why the Scripps faculty have called on us to develop a capability to look at how we adapt to sea level. So we have to know the basics of it, but we also have to partner with a huge array of other partners. You don't have to read all the words on here. It's really to remind me to sort of tick them off to you. Not only the physical science of sea level rise and how it affects biology, but also engineering and social science, and to look at how we adapt to sea level rise. Political science to navigate adaptation choices and to think about how we set up incentives to be able to adapt. The economics of adaptation. Education, for example, we've been talking with the School of Engineering about how they might work with us to establish criteria for training for people who are schooled in sea level rise adaptation. So this broad perspective of not only the science that we've been doing regularly, but also partnering with the rest of UCSD to bring in engineering, political science, economics, and other fields to come together with our oceanography to help our communities, certainly here in California, but around the country and around the world, understand how we're going to adapt to this. When you think about the percentage of the population that lives within the coastal zone, which is more than half of the world, you can see what a formidable challenge this is and how important it is that Scripps think about this. So I'll give you a couple of other little examples. One of them has to do with technology. So I talked about the impact of Argo and its in our ability to look at things. And we often think of wonderful coral reefs like this one and the damage that they're experiencing from a wide variety of stressors: temperature, pollution, physical damage from fishing, ocean acidification, and so forth, as an activity that has to be studied like this. That's a very labor-intensive activity, going out and being able to map areas, take pictures like this. But recently, one of our researchers, Dr. Eric Terrell, has been working with GoPro to develop ways of using little GoPro cameras that you can buy at Best Buy down the road to be able to take photographs of coral reefs, stitch them together with techniques like this to be able to take that 3D image of the coral back to the lab and be able to look at it go out again and map it in detail and bring that back to look at the differences. So also think about this in terms of all of the people that love to go diving on coral reefs, and think about being able to have citizen science re-photographing areas like this, stitching those together, and being able to have that wonderful view of coral reefs in a way that we never had the ability to do before. And so it's that combination of some modifications that he's made to GoPro, plus the ability to knit that together in a new way of much more powerful observation. That's sort of at a large scale. Let's look at an example at small scale. So another one of our faculty, Jules Jaffe, has developed an underwater microscope. And what you're seeing here is a 2-millimeter field of view for an underwater microscope that's being, that you can look at from your desk back at the lab. And I'm going to start the film here, and I'm going to show you why something like this can be so powerful. This is what this fuzzy image is 2 coral polyps, one on the right and one on the left. And these are corals that don't occur together. And one of the things that we were very interested in was why we never see them together. And so they actually artificially put them together, and then put Jules' microscope down there, and you're going to see what happens. So that's all of the coral polyps, and you're going to see the one on the left, or I'm sorry, on the right, sort of reach out and touch the one on the left. And what happens now, what you're seeing is that sort of cloudy thing. The one on the left has everted its digestive organ over the one on the right and is flooding it with digestive enzymes. It's attacking it. This is aggression at 2 millimeters scale. In the ocean with a microscope. So now think about the ability to look at things like this that we can't see and be able to look at them in real time from new techniques like this. And so another one of the areas that the Scripps faculty focused on was enhancing our ability for the faculty to be able to experiment with new technologies like this and think about each of these revolutionizing oceanography in the same way that the Argo Float revolutionized our ability to look at large-scale circulation of the ocean. And so those are some of the things that future scientists from Scripps will be getting up here in front of you to talk about in the future. It's really an exciting perspective, and it's an exciting way to think about understanding the planet. And of course, all of that feeds into our ability to provide the knowledge that allows us to conserve, to protect life and property on the coastal zones, and to think about these big issues like changes in the entire planet. So this is one of the ways that Scripps fits into that large frame that UCSD has identified for itself, a tremendous initiative, understanding and protecting the planet. Thank you so much. The question was, what's the lifetime of the Argo Float, and how do we confirm the calibration of it? Correct me if I'm wrong, Walter, but I think that the lifetime is on the order of about 5 years. And the calibration is very important, and there's during the time that it sends data back to us on land, it's also sending several calibration indices back to us, so we can see whether it's starting to drift and whether we have a problem with that. So, and so basically it's coming up to the surface where we know the temperature, and then it's sending both that measurement and a calibration signal back. Great question, and very, very important. That was one of the key factors in being able to put these out there and know that they were going to be reliable data. Okay, the question was, are the Argo floats recyclable? And yes, I should have made that clear. Each time it comes up to send data, after it's completed its cycle of sending data, it sinks again. So they're going up every approximately about once a week. So they'll go down, then they'll float with the ocean current, then they'll come up to the surface. So that recycles on average about once a week. And then the float itself also has many elements that are recyclable. So we have some of these wind up coming ashore, so they all have a little sign that says who they are and you know, call me. You can actually go on the NOAA website and you can track them by the individual ones, and for a while there was a program with school children to adopt an Argo float. So you could say, okay, you know, number 2369 is mine, I'm going to follow it, I'm going to like it on Facebook. So some of them come, you know, get trapped that way. Some of them fail, not that many of them. Some of them get picked up by fishing boats or whatever, and when they see one really start moving fast, it usually means it's been picked up. But oh, the question was, do we have any desalinization projects that would help California? We have something that is even more fascinating, and something I didn't get a chance to talk about, but that we also explored at the retreat. The big storm that's going on in Northern California right now is coming from what's called an atmospheric river. Some of you have heard of it as the Pineapple Express. And if you look at a satellite image of water in the atmosphere over the ocean, you'll see it as a ribbon extending across the Pacific, hence the idea of an atmospheric river. And these features form in the Pacific, and then they have higher concentrations of water vapor in the atmospheric river than on either side, and they move rapidly across the ocean, and when they encounter land, they bring that water with them. And one of our researchers, Dr. Marty Ralph, is probably the world's expert in atmospheric rivers. And what he has outlined is a program of studying of the rivers that would allow us to be able to forecast those with much greater precision and also further in advance. And why is that important for the drought issue? A couple of reasons. One is the reservoirs in California are by regulation forced to keep the reservoir level low during the winter, and that's with the expectation that the reservoir would fill up again during the winter. But the last few years, we haven't had enough rain during the winter to fill a reservoir. So what's happening is that we're artificially wasting water by not having the reservoirs full. If we could, and one of the reasons that there is this rule is that you don't want to have the reservoir full, have one of these big atmospheric rivers that's going to dump 7 inches of rain on you, and then be releasing water from the reservoir at the same time that you have a downpour. That's a life and property issue. So, but if we could predict the occurrence of atmospheric rivers 3 or 4 days in advance, we would be able to hold the reservoirs at a much higher level. And an economic analysis of this for California suggested that that's worth almost $350 million in economic benefit to the state from having that extra water for both people and for agriculture. And another, a group led by Dr. Ralph and Dr. Kim Prather of UCSD is out there right now flying through that atmospheric river and looking at what happens when it encounters land. And one of the fascinating things that they're finding is that a real key to whether or not that atmospheric river delivers a lot of water or not is whether there's dust in the air, because you have to have the little particles of dust in the air to nucleate the little ice crystals that then result in water. Otherwise, if you don't have the dust, the water just stays as water vapor. So such a complex relationship, but one that's being explored here and that has huge potential economic impact for California. Well, you can, but remember that there are two issues with desalinization that you have to overcome. One is it takes a lot of energy to evaporate water. Water has one of the highest heat capacities of any common compound. So you have to take a lot of energy to do that. And then second, you have a very concentrated brine or salt that's a residue of that. And then you've got to do something with that. And a lot of brine in the coastal zone would influence that environment. A lot of salt is something that we have to deal with, and we already have plenty of salt in our groundwaters and so forth. So I'm not saying we shouldn't do that, but there are big issues that we have to deal with for desal compared to being able to use the water that comes to us naturally much more effectively. Oh, the question was, could I reconcile the rapidly increasing cost of doing science with the rapidly decreasing budgets of agencies and so forth that fund science? First, on the cost side, I think that while we can, if you think about the technology and so forth, two things. One is that the cost of the technology is decreasing rapidly. So the Argo example is a great one. Contrast the cost of making that snapshot of the ocean versus the cost of Argo, and it's much, much lower. It's almost an order of magnitude less. And so we get much more bang for our buck today with modern technology. The second is in marine science, one of the highest cost elements is the cost of going to sea. So if we're able to not stop going to sea, but being able to use autonomous vehicles, AUVs, floaters, drifters, and satellites, a wide variety of different kinds of ways to get at the ocean, we can save those most expensive parts of oceanography, going to sea, for the times when we really need it. And I like to compare this to what it was like doing laboratory analyses when I was a graduate student. So if you wanted to measure the amount of nutrient in ocean water, you did wet chemistry. You poured one thing into another thing and you measured the amount of nitrate or phosphate. Today that's all done by autoanalyzer, and there's a continuous flow of water going through an instrument. The measurements are equally accurate, probably more accurate now than they were when I was doing wet chemistry. And we can do more of them cheaper. So that means that we save the expensive work for things that can't be automated or can't be approached in that way. And that's always the cutting edge of science. So we save the most expensive piece for the cutting edge, and the routine stuff we farm out to gliders and floats and other techniques. Then there's the issue of the availability of funding. And I think that several things. One is that it's of great concern that the U.S. has steadily decreased the percentage of its GDP that it's putting into research. And it's been able to really capitalize on the technology innovation and the ability to do more with less money. But we're beginning to see a couple of trends that are happening that are starting to add to that. One is that states are looking at the importance of scientific work to them. So California, which is the 8th largest economy in the world, is looking at issues like the science of atmospheric rivers and saying this is of direct importance to us, and we can see how we should invest in that. The second is that philanthropy is changing the landscape. And so in the past, we didn't have large philanthropists contributing much in oceanography, but now we have groups like the Schmidt Institute, the Schmidt Oceanographic Institute, the Gordon and Betty Moore Foundation putting very substantial sums into research in basic science in oceanography. So yes, it's of great concern, but the landscape is also changing at the same time, and it's one of the things that we have to adapt to. Sorry, that's a long answer, but the oceanographers are very interested in this. The observation was that it's a complex world, and we have everything from the mountains to the lagoons to the dry areas, rivers, et cetera, all affecting the coastal zone. And what do I think is the most important conservation issue for San Diego County? And let me give a disclaimer that conservation, biodiversity, et cetera, are not my own fields of research, and I've only been here a little over a year. But I would say that really, as in all areas, the big conservation issue, I think, is being able to balance the need to preserve areas that allow the environment to function properly with our need to use that environment. So I think that it's, while the conservation of a particular rare species or something is always of concern, the bigger concern is making sure that that environment continues to function in the way that we expect it to. So our wetlands and our estuaries are really filters. They're filters for everything that comes down from the mountains and from rivers upstream into the ocean. And so we expect those lagoons and marshes to continue to filter. If we've done things to that marsh or to that wetland that eliminate its ability to filter out nutrients, to filter out sediment from the coastal zone, then we affect our ability not only to use the wetland, but we affect our ability to use the coastal water and the fisheries. And so it's that trying to understand what part of it is the essential part that controls the stability of that habitat, that to me, as not a person in this field, seems to be the critical issue.
Margaret, I want to thank you very much for a wonderful talk.